Hello. In this video, I want to talk you through an example of the practical application of 3D printing and CNC machining to real-life problems. As you might have seen in my recent videos, I am trying to revive a Pelican PO kit that was first sold in 1995. I have touched every part and gone through every relevant page of the construction manual, and I have determined that there are 3 modestly significant parts that were in the original kit, which are now missing after shipping it approximately 2,400 miles. I say modestly significant because the plane will fly without them, but it will be better overall with them, safer in one case, and in 2 cases faster and better looking. The first part is the seat console cover between the seats. It serves to keep the elbows away from the innards of the trim and flap mechanisms, and it serves to keep stuff from falling into the cableway for the elevator trim, and rudder. Definitely a good idea to have aboard. The second 2 parts are the wheel pant support brackets. While not crucial, their absence means no main gear wheel pants, which will serve to reduce speed and consequently efficiency. Not only that, when I hit a puddle at the grass strips at which I often land, it'll keep mud off the bottom of the wing. The seat console cover will be shaped with my 3040 CNC in multiple steps, but it's not needed for some time, so I'll get to it later, even though I've already created the profile for it, made a 3D part, and made a test fit. The purpose of this video is to focus on the more difficult parts to produce, the wheel pant supports. While I have reported on my CNC efforts on this channel, I haven't said anything about 3D printing, except to provide a video to Tronci support to show that an upgraded bed level sensor I ordered was dead on arrival. This picture shows my 3D printing setup with climate control filament storage in the middle, which can simultaneously feed the printer on either side of it. I use principally ASA filament, with some use of nylon, Delrin, and TPU. ASA is my primary filament because most of my printing is for functional parts. So I don't want to have to worry about part warpage in a hot car like PLA, or early failure due to UV sensitivity for parts sitting in direct sunlight, also like PLA. To its left is a FLSun QQS Pro Delta printer, my first printer. The mechanics of the printer is stock. The stepper drivers have been changed to the silent types, the heat break cooling to quiet fans, the mainboard cooling has been changed from always on to thermostatically controlled, and the big change, modern firmware using Linear Advance instead of the stock firmware. Since I added a heated chamber for better processing of high-performance filaments like ASA, the extruder was moved from the top of the chamber to hanging from a stalk outside of the chamber. My main printer, which I refer to as my Frankentronci, is everything but stock, as it was purchased to encapsulate all of the learning of my first year with the QQS Pro. The frame is from a Tronci X5 SA Pro kit, giving it Core XY kinematics. That original frame has been reinforced with additional members. The original control board is in my basement, and this is now controlled by a Bigtree Tech SKR 2.0 32-bit board, which is handled through a 5-inch touchscreen, also from Bigtree Tech. The extruder is now in Orbiter version 1.0, direct drive for handling TPU, and is also able to push ASA very fast through a V6 clone hot end through a pricey, proprietary, but very effective Bondtech CHT nozzle. This printer also has a recirculating heated chamber and prints approximately 50% faster than the QQRS Pro at the same quality levels. Both printers have a fume scrubber attached with recirculation of the warmed air to maximize efficiency of the chamber heaters. Of course, the fume scrubber is mostly 3D printed, as are many components of the chamber frames, excepting the films or corrugated sheet and other accessories. Back to the practical application. The missing wheel pant support brackets will be created using skills I learned in a high school drafting class. The components in this drawing are very close to realistic scale with each other. Thank you, Jean-René Lepage. So all I need is a known quantity to scale the target part up to life size. That known quantity is the center distance between these two bolt holes. Given that data, extracting the key parts of the other dimensions was straightforward, and this data was recreated in Tinkercad. Since I was going to 3D print it first, I gave it a reasonable thickness dimension of 1.5 millimeters. The part was exported as an .stl, and using Cura 5.2, my standard fast and coarse profile was applied and sent to Octoprint and then on to the Frankentrancy. Using my typical frame per step time lapse, the video of its production is 0.24 seconds, but it tells the story, and it was done. Applying it to the main landing gear in the basement, it looked right. Comparing it to real flying examples sealed the deal. It was time to cut metal. This process came with many lessons learned the hard way, but I'm going to show it anyway. From Tinkercad, the part was now exported as a .svg. This time, SOCAM was used to prep the model for CNC by defining the holes to drill and the path to cut it out. 19 minutes was the estimated elapsed time. It could be done faster, but I used conservative numbers for feeds and speeds, and why stress the hardware if you don't have to? Now, for the many lessons learned with this CNC effort, I'll stop talking and let you see.